Okay. Again, thank you for having me, Vincenzo, and all you guys from ContinualAI. So I was invited to talk to you about my fairly recent paper that was accepted into IEEE Transactions of Neural Nets and Learning Systems, Continual Learning of Recurrent Neural Networks by Locally Aligning Distributed Representations. And of course, you see me on there, and then my co-authors and collaborators, longtime collaborators, Ankur Mali, Dr. Daniel Kiefer, Dr. C.B. Giles. I hail from Rochester Institute of Technology in Rochester, New York. And I've been working since August as an assistant professor in computer science. I started the Neural Adaptive Computing Laboratory, where we study, for example, biologically inspired learning, coming up with alternatives to backpropagation of errors for a variety of neural architectures. We also study extensively the lifelong machine learning problem and catastrophic forgetting or interference, and a variety of other problems as well. Also recently been diving into spiking neural networks, which I will talk briefly about in this. So this talk will, while it will largely center around this journal article, I will actually connect it to the larger body of work from which it exists. As I was talking to Vincenzo earlier, I saw that you guys are aware of a couple of my other papers. I'm more than happy to talk about those to you guys in the future, but they are related in some way to this. This will focus on temporal learning and a little bit of the continual aspects, but I'll actually show some results from some other recent papers that kind of provide some context. So let's dive right in. So what is the problem? Well, one of the things that we're interested in statistical learning is to train neural temporal generative models, ideally without unrolling. What do I exactly mean by unrolling? I realized I neglected to put a little diagram, but I'm sure all of you are familiar with backpropagation through time, which is the workhorse algorithm used to train recurrent neural networks. Again, it is no different than simple backpropagation or reverse mode differentiation, but what we do with a recurrent neural network is the hidden layer or hidden layers, if we're talking about a simple RNN, is technically unrolled or unfolded over time to create an equivalent deep feed-forward neural network with multiple inputs going at every time step. And then, of course, once we do this act of unrolling, of course, usually, ideally, we want to unroll this network over the entire length of, for example, an entire sequence, such as a sentence composed of words or characters, or perhaps a video composed of pixel frames. The idea is then we want to calculate gradients for the weights. And of course, an RNN is one of the more efficient approaches to doing an unfolded training regime where we share parameters through every step in time. So I won't bore you with the details of a review of backpropagation through time, but that is the goal. And that's actually largely where the paper that I will be mostly talking about in this presentation tries to get rid of. I will also talk about backpropagation in general, and from a biological standpoint, we know that the brain is highly unlikely to do backpropagation the way that it's implemented in modern day feed-forward neural networks, artificial neural nets or ANNs. I will try to keep myself from making too strong of a claim to say exactly how the brain might do learning, since that is largely an open problem and very complicated. But again, I think most of us can agree that the way that backpropagation is implemented is unlikely how neurons probably transmit information and adjust their synaptic weights during learning when trying to gain experience from sensory patterns. So the idea is that we want to find a different approach to learning and inference that yields recurrent models that learn in an online fashion. And again, backpropagation through time, while again, you could argue does work in some sense in an online incremental fashion, the unrolling aspect is quite pesky. And again, I'll mention that the brain is even more unlikely to unroll. So the problem that we're also trying to think about is that when we add a temporal dimension to data, the underlying distribution is evolving. Typically, again, many of the state-of-the-art networks are trained on static patterns. So again, ImageNet or larger data sets. And the idea is then we'll backpropagate these deep feed-forward, maybe residual networks. to get state-of-the-art categorization performance. But what if the parameters of the underlying data generating process change with a function of time? And again, this could apply to static distributions as well, static patterns, where maybe the categorization pattern, the labeling scheme of the data might change with time. And so again, hence why catastrophic interference occurs as we train a feed-forward network even on a simple problem. Maybe we have two data sets and we switch from task 1 to task 2. Well, the feed-forward neural network forgets all the information that in knowledge it has acquired on task 1. So again, it's kind of a long-standing grand challenge to try to get an agent to learn across tasks. And again, also to learn through a temporal dimension as well. The long-term dependency problem still plagues recurrent neural networks, even though we have a vast array of different types of architectures like the long short-term memory and friends and the delta RNN and different models that try to, attack this long-term dependency problem. But it is in some sense related to the forgetting problem as well. And again, patterns are usually more complex, so we could be dealing with natural language text, like sentences, words in a sentence, symbols, or for example, characters, frames in a video, speech patterns for speech signal processing. So what is our general idea in our direction to getting rid of unrolling, for example? Well, we propose continual error correction. And this kind of mechanism falls out of a general framework actually coming from computational neuroscience and neuroscience research in the idea of the theory of predictive coding, where we might be able to construct neural architectures that learn to adjust themselves at every step in time. And again, this can apply to static data as well. And I will show you towards the end the broader picture, how the framework that we're going to look at for the continually learning recurrent network applies to a variety of other architectures as well. And I'll also present some results on 0 and 1-shot adaptation, a little bit on continuous sequence modeling, and some other interesting results along the way from other papers over the years. So, problems with backprop. And I'll try not to dwell too long on this, but what's the key problem? And here's where I hope my cursor is at least partially visible. You'll see in red here, I have an autoencoder as just one example. It doesn't have to be an autoencoder. The global feedback pathway is typically how we train a general feed-forward architecture. And again, in red dashes, we essentially will take maybe some type of loss function. Let's say it's the mean squared error. So we give the autoencoder X, we run it through the model, try to predict X prime as labeled here. This is actually the first derivative. E0 is just the first derivative of the mean squared error with some other assumptions. But of course, what we'll do is we'll take this little error signal and we essentially pass it back through all the layers of the network. Again, creating this very long dependency chain and creating many problems that are very well known in the literature, like vanishing and exploding gradients. And again, this highlights actually what defines a lot of deep learning today, where we need a lot of tricks and heuristics. And again, as I have at the bottom of this slide, one of those key limitations of the global feedback pathway approach, or backpropagation, is we essentially have to design our artificial neural networks to appease backprop itself, the optimization process, instead of for the problem task at hand. So again, we need things like batch normalization, layer normalization, and a variety of many tricks that have been developed in initializations over the years to get backpropagation to work stably. There are some other problems that are also a little bit more of a neurobiological nature. The weight transport problem is well known, where essentially as we work our error back along this network, we have to take the feed-forward weights and use the transpose to essentially carry that signal or backpropagate it back from one layer to the previous. The brain doesn't necessarily actually do this. It's not known that the synaptic feed-forward weights actually carry the same signal that was transmitted forward backwards as an error signal. So the idea is to perhaps get rid of something like that. Many of you might have heard of the random feedback alignment and some other recent algorithms that have come out from Timothy Lillicrap and others. We have investigated those as well in the context of some of our own learning, and I'll mention some citations to other work that tries to get rid of that problem as well. Neural nets are highly sensitive to initialization. And again, like I said, that's part of the tricks to get backprop to work right, and requires heavy constraints. You might be familiar with adversarial examples where we can perturb a sample just enough with actually the gradient information from backprop to actually get the network to misclassify. And again, while this is, in my view, an AI problem, since the neural network should be able to be recognizing an image more robustly, even if we perturb a few pixels, this has actually launched a whole branch of research in computer security, as we want our networks to be reliable and maybe not tricked by, some adversary or some malicious actor. And of course, as well, for backpropagation to work, since it's essentially just the chain rule of calculus, the network has to be fully differentiable. So that means the activation functions and other mechanisms that you put into your network must obey the framework of backprop. If it's not differentiable, you can do weird approximations that might allow you to trick it into training something that's discrete valued. But other mechanisms that are nonlinear and brain-like, and ideally perhaps useful for combating things like catastrophic interference, which we have shown in some work I'll mention later, they're very difficult, if not impossible, to integrate into the standard networks of today trained by backprop. So backprop essentially needs to go. And again, how might we begin to start thinking about this? Well, we see to the left our initial graph with the full global feedback pathway. And we see to the right the same type of autoencoder and structure, but maybe formulated as a local optimization problem. Again, we could still use backprop as an intermediate step to kind of get ourselves to a more general learning approach. And again, by the way, another thing that goes without saying is that the brain largely learns with local signals, usually with something that's Hebbian-like, and information that's readily available to neurons in the spot that they actually physically exist in. Neurons usually don't typically wait a long time for other neurons to transmit error information to correct themselves, at least with the current state of what we know in computational neuroscience. And so we might be able to formulate the autoencoder as a series of local losses. So we have some error neurons perhaps embedded in that compare layers across from each other. So if we think of the autoencoder as maybe an encoder to the left and a decoder to the right, there's a symmetry here that we could exploit. We know that the model is going to predict X, which is the input, so we could compare it to its input. And we could also compare the decoder's layers to the encoder's layers or vice versa to create some type of learning signal. I've mentioned the term error neuron. I will define this a little bit more later. But the idea here is that we'll just have local losses or local signals that compare representations. However, there might be an issue with just naively formulating an autoencoder like this. Will this yield a coherent model? And again, you can see I've labeled the global feedback pathway to the left. And to the right, I've just noted that the idea is that we're not entirely sure if just maybe naively formulating this model will work. Well, it turns out that the answer is yes, it will yield a coherent model, but with some qualifications. So what I showed earlier in this slide here is that these are local rules. Again, they just are somewhat entirely independent of each other except connected through the feed-forward pass. Coordinated might mean that we might need some structure or some synchronization between the local losses and the different layers. And again, this kind of leads us to formulating architectures that somewhat connect their signals, again, though, with other mechanisms than the reverse mode differentiation that's used in backpropagation. And I have some citations here with target propagation and variations. Local representation alignment was something that we came up with in 2018 through 2019. And recently we have out this year a much more large-scale version of the algorithm that allows you to train things like residual networks. These actually come from the same framework I'll be talking about today, discrepancy reduction and the idea of predictive coding. But these are largely focused on feed-forward networks. So what are our neurological motivations? I've already mentioned a few of those, like the weight transport problem. But again, the key idea is that why might we want to look to changing what it works so well in most of deep learning, backpropagation, well, if we can look at maybe at least draw further inspiration from how the brain might actually conduct learning, we might free ourselves from the constraints of backprop. As I mentioned earlier, training with discrete neurons or even stochastic functions like Bernoulli neurons, and let alone spikes, which actually define how neurons really communicate in the brain, are almost impossible in a backpropagation framework. We might be able to design powerful mechanisms to fight big problems like catastrophic interference. And again, this kind of implicitly lies on my own hypothesis that a large part of the problem behind catastrophic interference lies with the learning algorithm that we use. Again, it centers around challenging the paradigm of backpropagation, but there are other problems as well, and other factors like how the architecture works and how introducing modules of memory. We also know that the brain does multiple steps of processing. And again, here we now kind of zoom you in a little bit to a little bit of the theory that guides my research. Again, it's the theory of predictive coding. The idea is that the brain does an active kind of approach to learning from sensory input. And again, this can be extended to action and reward for reinforcement learning. But the idea is that the brain passes bottom-up and top-down messages or signals across different neurons in a local fashion. Now, there is a coordination across all these layers over time, and there's significant evidence of complex recurrence and lateral connectivity. Again, both concepts that are very difficult to integrate in most backpropagation-based frameworks. But the idea, in short, of predictive coding, and again, we see it, I've cited some of the seminal work in the area, again, some classical papers from 1999. Many of you some of you might have heard of Carl Friston, the free energy principle. Another idea that kind of you could use to think about the optimization framework where I'll present to you shortly. But the idea is that the brain actively guesses what's going to come now or what at any time step. For example, it could be the pixels of an image. These could be varying in time. And the idea is that it'll guess first and then correct later. And again, this is different than a little bit than the feed-forward paradigm we might be used to, where we're learning an input-output mapping. So we're taking an input pattern and running it through a feed-forward network, perhaps, or some kind of feed-forward directed structure, and gathering the statistics. So the neurons in this case actually technically don't exist until we clamp data to our feed-forward network. Again, a recurrent network is a feed-forward network just unrolled through time. And then we gather the statistics and then do backpropagation to update the weights. But maybe we should start thinking about formulating our neurons from a more stateful approach. And again, recurrent networks are a good stepping stone towards this direction, but neurons in general are always active. They always exist. They're not null before presence of data, as we know in spiking literature as well, that they have a resting rate as well. So maybe we'll add a state to them and imagine that the brain has an internal state and it needs to adjust itself when in the presence of data. And so I'll show you this shortly, but I just want to briefly add, since I've seen some of your prior talks on sparsity. Sparsity is very important, as you've seen before. And we'll also talk a little bit about it in this. There's some other work that I have that actually gets a little bit deeper into this topic. Sparsity has so many benefits, especially for memory retrieval when we're trying to tackle problems like forgetting. But again, the predictive coding paradigm also shares some nice connections with sparse coding from the great work of Olhausen and others in the old days. And so introducing sparsity is a component in this framework and many of the other things that my team does. So again, does the brain unroll itself in time? Well, no. At least not maybe in the way that, again, we actually explicitly unroll recurrent networks in the literature today. So again, the idea is that we want to get rid of backprop. We definitely want to get rid of backpropagation through time. And I'll also mention, and we do compare, and I'll mention some results today, sparse attentive backtracking and truncated backprop through time. While they address certain issues with backprop, they are still backprop at the end of the day. They might have fancy mechanisms like an attention mechanism, as in sparse attentive backtracking. But at the end of the day, you still have to take gradients with respect to some loss that's attached to the output layer of the network and pass back the signals through time. And truncated backprop just deals with the fact that we don't want to unroll the network over the entire sentence. We unroll it over some small window, which introduces its own problems. There are online alternatives, and you will see them appear in our results later. Echo state networks, which actually have some nice properties that are neurobiological. At the end of the day, echo state networks essentially you could look at as a specialized type of recurrent network where we just train the output weights, and the internal weights, the recurrent connections, input to hidden connections, and others are not tuned, they're fixed, and they are essentially carefully initialized to create reservoir dynamics. So this kind of comes from a broader range of alternatives called reservoir computing. They're very powerful, but again, it seems unlikely that the brain will not train most of its own synaptic weights and only just a few. So that would be nice. And also, again, echo state networks, and we found this, we kind of say this more from experience, from an implementation standpoint, they require a significant amount of time to really get those reservoirs initialized and tuned carefully to get optimal performance, which is not ideal if we're trying to build somewhat of a general robust agent that can learn from pattern streams. Real-time recurrent learning is, again, a differentiation-based approach, but instead of doing backprop, we're doing sort of like a forward differentiation version of backprop. Again, it's still based on the rules of calculus, but the idea is that you can construct an online update. However, the memory costs and requirements for this is incredibly expensive. If I'm asked, I have, and also in the paper's appendix, I have a table comparing their run times, doing a complexity analysis, as well as their memory costs. And RTRL is a pretty nasty algorithm. But it is an important algorithm to talk about as it offers an online approach. Euro, or unbiased online recurrent optimization, and other ones known as backtracking and other algorithms are approximations to RTRL. They try to make it faster, and they do indeed reduce some of its costs, but it's still gradient based. And we also have to now deal with the variance of the gradient estimate, as whenever you develop a learning algorithm, you have to deal with the bias variance trade-off. So if you get no bias, then you incur variance. What's the general takeaway from most of these algorithms? Online updating is often a bug rather than a central feature. So again, thinking back to our idea of continual error correction, and the idea of that the brain is more active in its approach to dealing with sensory data, why don't we instead make the online learning a central feature, or at least the iterative updating? And the idea is that we want to minimize something called total discrepancy, which is the general optimization framework I'll talk about here in this talk. And actually, when you formulate the objective like this, it actually yields, through derivation, a nice continual error correction scheme and local update rules. So in many ways, we take care of many of the problems with backprop, check most of those boxes in one fell swoop in one nice framework. Now, this doesn't solve all the longstanding problems. There's still a lot to do in making the framework more neurobiologically faithful, but it does take care of some issues like the weight transport problem, the need for differentiable functions. So what does this kind of look like? And so I'm not showing here exactly the architecture used in the IEEE paper. I'm showing a simplified version just to kind of get your minds around the idea of local continual error correction. So in early work as early as 2017, we talked about maybe thinking about the learning and inference as two intertwined processes rather than sort of two separate approaches that might interact. Like backpropagation says, okay, we've done feed-forward inference in your network, and then agnostic to however that inference happened, we're going to calculate gradients going back along that pathway. But maybe instead we should think about that learning and inference happen all the time. Now, I will present results where I fix the learning at test time, but the idea is that a true learning agent, and if you think back to how humans might learn, we're constantly updating our synapses given our experience. If we think about sequences, since we're talking about that here, if I'm having a conversation with you, I'm constantly guessing the next word you're going to say. And as I build my internal model of our conversation and my mental model of the agent that I'm speaking with, I'm constantly adjusting. Now, again, it might not be severe adjustments, There are different degrees of how synaptic weights are adjusted. And actually, as I saw in one of your earlier talks, even weights are being pruned and grown even in adults as we learn. But the idea here is that we want to kind of formulate the computational process of learning and inference as kind of two steps. Search for latent representations that better explain input and output variables. So again, this could be formulated as an X to Y problem if you're doing classification, or it could just be X if we're learning a stream of sensory input patterns like video frames. And then once we have a latent explanation for a particular pattern vector, X of t, as shown here in the slide, we want to reduce the mismatch between our guessed representations and what we call target representations, or essentially activations for every layer that better explain either the mapping from X to Y, or better explain the causal nature or relationships of latent factors that might give rise to the sensory pattern that the neural agent is looking at. So what I have here on the right is essentially a top-down directed two-layer version of a temporal neural coding network. In the IEEE version, it's P-TNCN because it emphasizes the parallel computations going on in the network, and there's a couple other extra things. But the simple temporal model here, you can see we had introduced recurrent weights, V2 and V1, and these are what label the directed edges. So again, I show 3 neurons in every layer here, and so these directed arrows are actually weight matrices. So just bear that in mind. I'm collapsing a lot of things to make the diagram look clean. And the idea is that we also have generative weights, W2 and W1, that map a hidden layer at any time step t and generates a prediction of the input below it. And so what's kind of neat here, and I'm already kind of showing you before even looking at the objective function, is that we have a network that is local in nature. You have 2 hidden layers. We have a sensory layer, X, so of course this is where you would put pixels of a frame of a video, or a one-hot encoding of some symbol in a sentence. And the idea is that we've also introduced this other little guy, I've mentioned it earlier, the error neuron. There's a lot of significant evidence in the neuroscience literature of neurons that are involved in cortical regions of the brain and other areas that essentially are just tasked with computing different signals or error signals or mismatch signals. And the idea is they say, I take in some input, maybe from some other set of neurons that are fired across other synapses, and I compare it to something that I immediately am forced to look at. And again, if you have sensory neurons at the very, very front edge of your eye, obviously they're comparing it to what's being stimulated directly from beams of light. And again, we can think about it as that Z1 in the diagram to the right is generating a prediction of X. So what E0 is trying to do, and again, X would be Z0 if we wanted to label this consistently. I will do that later in the animation slide. The idea is that it will just compare the difference between layer 1's prediction and X. However, the layer above it is trying to guess, instead of maybe being connected and hardwired in a raw feed-forward fashion, as you would construct maybe, for example, the decoder of a variational autoencoder, Z2 is tasked with not predicting X or being connected feed forward. Its goal is to predict Z1 itself. So actually, if you think about it, that means these neurons have to have a state, and it has to exist across time. So even if there's no input patterns being presented to the network, you have to imagine that these neurons are initialized at least to an activation of 0 or some base rate activity. And the idea here is that neurons in layer 2 guess the state of neurons in layer 1, which are readily available since all the neurons are active all the time. And again, they don't necessarily, when I say active, that means they exist. It doesn't necessarily mean you have to be firing. In fact, actually, most of these are very sparse activities, again, in adherence to actual brain firing patterns as well. And the idea is that these are also recurrent. So again, they are dependent on their previous states. These recurrent weights could also be viewed as lateral inhibition weights if we're processing fixed input. And that has a nice interpretation I'll mention a little bit later of expectation maximization. And the other thing I just want to make brief note here is that we've also introduced another set of weights called error synapses. So while every layer tries to generate a prediction of the layer below with some forward weights, and it's also conditioned on its previous state with recurrent weights, we have these error weights that try to transmit the error signal from the error neurons. And remember, all the error neurons are going to do is compare the prediction of the layer above with the actual input target, or again, if it's layer 2 predicting layer 1, it just compares its prediction with layer 1, and it's going to transmit that signal back to layer 1 if we're doing it from layer 0. So this is the message passing scheme. And then there is a top-down interaction, though, with the error neurons from layer 2 to layer 1. And again, this pops out from the derivation of the cost function. And what you end up doing is you create a target representation. This can be used to adjust, for example, the recurrent weights, which are trying to guess the state of layer 1. And you can do a lot of other interesting things. And I'll get more to these derivations here soon. So again, you could start to think about as a feed-forward network as a set of linked subgraphs coupled by error neurons at every layer. And the error neurons work to minimize error they receive from below as well as error from above. So there's a top-down expectation from layers above trying to say, well, the brain has maybe some current idea or impression of its environment, and it's transmitting its guesses downward towards the sensory layers. And then the sensory layers actually pick up real information or clamp to data. And there's a bottom-up kind of message passing that kind of interacts with the brain's expectations. So just briefly here is a kind of a quick diagram. I'm omitting the recurrence weights for sake of simplicity. Let's just say we have a 3-layer network, 2 hidden layers, again, just like the diagram earlier, but now you can actually see the synaptic weight matrices made explicit. So we only have 2 neurons because we want to keep this diagram as little clutter as possible. The red diamonds are error neurons. And again, there's 1 error neuron for every neuron in a particular layer. So again, these are layer-wise as well. So you'll see a prediction being made here and an error neuron trying to compare the prediction with the latent state. And the bottom layer, of course, will be clamped to input data. So in this case, we're dealing with images of 2 pixels, which is really, really funny because there's no such thing. But the idea is for sake of example. So we have these neurons. Let's say they're initialized from some previous state or they're initialized to 0. They make a guess. So they're going to produce their predictions of, for example, layer 1 tries to predict layer 2. Tries to predict layer 1, and layer 1 tries to predict the sensory input layer. And right now it just generates its guesses. The error neurons do a comparison, and in this case it can be something as simple as just a subtraction if we're doing something like mean squared error as a local loss function. And the idea here is then they say, okay, we have our mismatch signal. Now we need to change the hidden states themselves, so layer 1 and layer 2, in light of this error information. So we propagate them back up. And so the idea here is that there's going to be those error synapses that I mentioned earlier, big E, that carry, for example, the error information at layer 1 back up to layer 2, and error information at layer 0 back up to layer 1. I have green diamonds here to show that if, for example, we need to adjust the states of these actual neurons. And so the way that's done is we have propagated the information above, and we're going to take the current state of the neuron and do some type of correction. It could be something that looks very similar to like a Kalman filter or a gradient step update. And the interesting thing is that then this process repeats. So if we had fixed input, we would run this k times and converge to some optimal set of latent states or a fixed point, if you want to think about this like an energy model. And the idea is that this optimal state can then be used to say, all right, now we want to adjust the weights given any remaining error in the error neurons. So again, you end up using the same error neurons to adjust the synapses as you also use to correct states themselves. Again, if this is temporal data, you don't need to wait for a fixed point as the P-TNCN does. So again, the total discrepancy, which is again the sum of mismatches across the entire network or across all layers, is just a sum of internal losses. This will be in NATS since we're thinking about this from a log likelihood framework, but doesn't necessarily have to be that. And kind of at a high level, what we're thinking is this top-down model is a directed generative model, and we want itself to guide its own inference. So instead of having something like an encoder, a decoder, and a variational framework, you could think of this as a decoder that just guides itself, with these error synapses serving as a way to pass messages along the different layers in a local fashion, because as you can see here, E1 just connects layer 0 to layer 1. You can do more exotic error connection patterns, and actually that's what I had in my citation earlier to recursive LRA. You can build skip connections in the error messages as well. Again, if you have fixed input, this equivocates to an EM algorithm, and we can also make X of t temporal. So what would this network look like from a temporal standpoint? Well, let's look at the bouncing ball problem, which I'll show you a few results shortly. Let's say that the network is trying to guess the dynamics of balls bouncing around in a black and white grid. And the idea here is that the network generates its own guess. Of course, here you can see from being initialized at 0, the guess is pretty poor or random. And the actual ball state is obviously to the right. So the error neurons will do this comparison and transmit this information to correct the state of Z0. Now Z2 tried to guess the state of Z1, so it will also do that correction as well. And then if we have recurrent weights, we will compare the difference between the corrected state and the old state, and that gives us a learning signal for the recurrent weights. And this process happens per time step, all the time throughout the processing of a sequence, which could be infinite in nature, because there's no necessary reason to think that the sequence might end if it's an agent processing sensory stimuli from an environment. So total discrepancy can kind of, and I won't have too much mathematical detail in this talk, that could make this very long, but the idea here is that you could think of the loss as, again, like I said, a sum of layers, sum of layer losses. So here I am showing a generalized distance function, but if you set p equal to 2 and q equal to 2, you have mean squared error. And the idea here is, again, we're summing along dimensions j along a vector. So let's say every state vector z is compared to some prediction of it, which is mu of L. And again, mu would be essentially the neurons being carried from layer 2 to layer 1, and layer 1 to layer 0. So again, we're looking at differences here, different signals. And again, this can be kind of made more explicit. To the left in this loss function is the sensory input loss, and here's all the latent variable losses or all the internal losses of the network. What the network is trying to do is minimize this entire cost function or this entire objective function. And of course, if I were to specify this for a feed-forward network, you would have the problem of, well, what are the targets for the hidden layers if we are not doing back-propagation to create a teaching signal? And that's what some of the earlier citations were trying to introduce a generative structure to do this. But in this generative network here, we have for free the targets. So actually, readily at every time step, this network has the adjustments that it has the targets it needs to make its adjustments, and it can also correct its states dynamically. The error neurons at a high level are essentially derived. You essentially embed them. They actually do exist as a physical mechanism in the network, but you derive them based on your cost function. So while I show a generalized distance function here, if you're taking the mean squared error, that amounts to simply just subtracting the prediction of a given layer from the target itself. So again, those are what those error neurons ends up being. And then those essentially are what kind of drive the learning and inference of the network. So the P-TNCN is pretty much exactly the network that I described to you, with just a couple of extra things. So what I show here to the left is the network with its recurrent weights, again, at every layer. This is still the same 2-layer network. And inside the box, you can imagine there are multiple neurons. And in the previous time step, you can see that it was conditioned on whatever the state was for the last input at t-1. I've labeled these as y because these are actually corrected states from the previous time step. The thing that's different between this and the network that you've been seeing in the previous slides is I've introduced a set of autoregressive weights, which kind of make this look a little bit like a recurrent network. So layer 2, latent variable layer 2, Z2, is conditioned not only on its previous state, or corrected state, but also on the corrected state of the layer below it. Of course, layer 1 is also conditioned on the previous time step input. So again, if we're thinking of the bouncing ball problem, it's the pixel frame from the last time step. And then the other interesting component is that Z1 is also conditioned on the corrected state of layer 2 in the previous time step. So we have another like autoregressive sort of weight, U1, and essentially that's carrying information in a top-down fashion. So we have the error neurons implicit, and I'll show them to you as we work through this diagram. And then we also have these weights carrying sort of immediate signals from layers nearby. Again, this is still local in nature, and the nice property about the P-TNCN, or this network, is that these layers can be computed independently of each other. So at any time step, layer 2 does not require knowing what the state of layer 1 is. And layer 1 does not require knowing what the state of layer 2 is. And again, the equations taken from the paper illustrate what this state of the diagram is doing. So you can see here we've labeled the pre-activations of every layer, A2 for Z2 and A1 for Z1. I'm just not drawing them on the diagram here for simplicity. We have a recurrent projection of the last time step, y of 2t minus 1, plus the autoregressive connection of the corrected state below. And then we run it through some activation function phi of z. This could be tanh, or it could be a discrete function like the signum function or the Heaviside step function. And then layer 1 is pretty much the same as layer 2, except we also have its top-down autoregressive weights, kind of carrying the corrected state above. And we run it through its activation function. And obviously layer 0 is clamped to the current pixel frame that we want the model to try to predict. So then the next thing we do is we generate our predictions. And again, we use a different set of equations that actually amount to essentially doing a conditional probability. In the paper, I show you what the graphical model that this derives from. But the short message is that we take layer 0, we multiply it by a weight matrix W1, run it through some activation function, and now we have our guess of layer 0, which is also mu of 1, mu of 0. I should have labeled that, and this should be mu of 1. My apologies, for consistency with the previous slides. And the idea is that this is the guess of the input layer, and this is the guess of layer 2 of layer 1. So we're just doing simple matrix multiplies here. And the error neurons, which are derived from the objective functions shown a few slides ago, essentially amount to comparing the predictions of layer 1 to layer 0 with the actual input, and also layer 2 to layer 1 with the actual state of layer 1. And again, this is computed in this case where saying that these error neurons say, all right, now that we've computed in parallel the states of the network, we can do this like synchronized step where we compare the mismatched signals. And now we have our error signals to actually adjust states and adjust weights. So what do we do next? Well, we project those error messages, like I said a few slides ago. We use our error weights E1 and E2. And E1, as we can see in the equation here, just projects the error message. E1 projects the error message at the input layer. It also combines it with the top-down signal of E1, which, again, it's essentially just the same difference function, but the negative version, this plops out, again, when you derive the error neurons and the updates to the hidden layers from the total discrepancy function. And again, you can see here, layer 2 is just projecting the error neurons from layer 1 back up. And we're adjusting the pre-activation that already exists for that layer with a weighted version of that delta signal. And all this term to the right here is our sparsity prior. This is kind of motivated from predictive coding. In lieu of introducing lateral inhibition weights, we can introduce a factorial kurtotic prior that encourages essentially just the latent variables of the neurons. Most of them, we want them to be 0 and only a few of them to be non-zero. So that way we have a sparse activity pattern. And then we take this new perturbed pre-activation function and run it through the activation function again. And that's what gives us our new corrected state for time step t. And so then after that, we would move on to the next time step, because now y of t of 1 becomes y of t minus 1, and y of t of 2 becomes y of t of 2 t minus 1. And we just essentially repeat this process along the length of the sequence. And again, we can compute the updates to the weights immediately for every time step, because now we can use the error neurons computed by the red diamonds, and they essentially amount, when you derive them, to just a error Hebbian rule. They are just a product, and there's actually a matrix multiply here, so there would be a dot with the transpose of the activities above. So you can actually use your favorite optimization framework. I mean, we usually use stochastic gradient descent, but ADAM and RMS prop and all the other nice tools from deep learning apply here as well. So I wouldn't call these gradients, because we're also omitting some derivatives that actually don't need to exist, because it turns out as long as your activation function is monotonically increasing, or if the stochastic function is a monotonically increasing distribution, the derivative actually doesn't do much to the actual learning signal, and actually you can omit it very easily. So actually we get a derivative-free update. And it turns out actually this converges a little faster, weirdly enough. And then, of course, you can update the autoregressive weights, M1, U1, and M2 using the same error neurons. Of course, here we're showing that you're using the error neurons that compare the corrected state with the original state of T2. And so you can adjust them that way. You can also replace them with the error neurons. There's a couple different interesting configurations for this model. And then, of course, the recurrent weights get updated by comparing the corrected state with the original guess state. So you get pretty much, you use these error neurons and the difference between corrected and original states to get for free local learning signals. I'm not showing you the error update rules for sake of time, but again, these just show you the comparison between the corrected state and the previous state. The error weights in the original paper are updated through like a temporal error difference rule, but it turns out actually you can get a better rule that works and converges faster by essentially just doing a symmetric transpose of the weights for the forward weights. So it ends up working out that if you just take a product of the error rule above and, the error neurons above and the latent state below, you can update the error weights very quickly. More details are in the paper, since I obviously am going through this a little bit fast. You can also combine these with a actual Hebbian update, which is nice because it shows that we could learn some correlations across neurons as well. So correlation learning comes back into play. I tend to view the Hebbian update that's introduced in the IEEE paper as a light regularizer, but it worked to improve our results just a little bit, and it adds some nice connections to work by Randall O'Reilly and others. So again, the network just essentially looks like this. We see our old time step. We're going to correct it. We propagate it to the new time step. The green diamonds here are those little error neurons I told you about earlier. And as we see here, we see some samples from Bouncing MNIST, which is the benchmark that we use to test our networks in the main paper. Actually, you can see some samples from Bouncing MNIST here. Bouncing MNIST is often used with long short-term memory and a bunch of other recurrent networks. So we do comparisons to those. And again, we also created in our paper 2 new benchmarks that essentially just mimic the process of Bouncing MNIST by taking not-MNIST, so characters instead of digits, and clothing items from fashion MNIST, bouncing around 2 objects or 3 objects or 1 object, and having, again, the neural model try to guess the state of the next video frame given past information. So again, briefly, we can see that actually the P-TNCN actually outperformed on all the video prediction problems, not only backpropagation through time, training a GRU or an LSTM, or using fancy alternatives to backprop like sparse attentive backtracking. As I told you earlier, it's also still a gradient-based approach in some other benchmark models above. Again, we usually measure cross entropy or squared error on this benchmark. So again, we see, that the best RNN gets like maybe about 85.18 squared error, and we actually outperform it, getting a squared error of 79.67. And again, admittedly, you can always improve these results further with additional tuning. We did train a network with about 1,000 neurons in every layer or so, if I recall, 3 hidden layers. Again, though, the thing that's nice about this is that the P-TNCN has no unrolling or unfolding at all. It works at every time step, very much like we would expect a real biological agent to process input, making corrections to its neural state variables at every step of the way. It guesses first, so we're able to compare it to a predictive model. We're not cheating by doing on autoencoder reconstruction, but then the model is able to use the correction at every time step to adjust its hidden state. And then as also in addition, when you're training, it's able to adjust its weights immediately. It doesn't have to wait for you to pass through the entire sequence and then backpropagate signals. We also have here an echo state network, Euro and RTRL, as I mentioned to you earlier. Those are other online alternatives to backprop, but they're incredibly slow or have their own problems. You can also see that we also did well on Bouncing NotMNIST. Penn Treebank was our way of looking at discrete variables, and we did character modeling, so we did bits per character. Details are in the paper. We did not actually outperform backpropagation through time, though we did get close to the GRU and the LSTM, which has a BPC. Again, this is the simple models. State-of-the-art on Penn Treebank is much lower with the very, very fancy memory nets and other architectures. But we're not too far away, which is very encouraging. And more importantly, we outperform all the online alternatives, which are vastly more expensive in their computational and memory costs. So there's a little bit of room for improvement for discrete variables. And again, if you use different update rules, actually it turns out, not in this work, but in subsequent work, you can actually improve your results. I'm also putting here for completeness results from 2017 on the bouncing ball problem. It's a little cut off here in the slide if you are seeing the share screen thing, but turns out that you can just look down here. The 4-layer version of the temporal neural coding network gets a squared error on the bouncing ball problem of 2.55, beating out restricted Boltzmann machine models and multi-layer Boltzmann machine models, sigmoid belief networks, and even sigmoid belief networks trained with variational inference. So actually even outperforming variational autoencoder-like models on the same problem. So that was nice on that little benchmark. To the right, I just put for a little fun. A thing that's interesting about the neural coding network is its ability to generalize seemingly out of sample, or rather out of domain, I should say. So the bouncing ball problem is originally a 3-body problem. So there are 3 balls bouncing on the screen. So we, of course, train it on the 3 balls. And then what we did was we created our own generator to generate a 2-ball and a 4-ball problem and just tested a trained RNN and a trained neural coding network that were trained on 3 balls. How did they do on 2 and 4 balls without any extra training? So this is 0-shot adaptation, meaning that they must take their knowledge of objects gained in the 3-body problem to generalize to a fewer number of objects or a greater number of objects. And while the error does increase, for example, when you increase the number of balls, the temporal neural coding network actually outperforms an RNN trained with backpropagation through time. Again, this was an old paper, so we only investigated for proof of concept of a simple model, and there are better variations of the neural coding network today that would improve its own error. We also have some continual sequence modeling results, and really in short, what we did to construct this experiment was we took 3 tasks. We took Bouncing MNIST, Bouncing NotMNIST, and Bouncing Fashion MNIST, and we said, okay, we're going to train the neural coding network and an LSTM trained with backprop, SAB, and RTRL. We'll train them on Bouncing MNIST first, and then we'll train them on Bouncing NotMNIST second. I believe it's, yeah, NotMNIST second, and then Bouncing Fashion MNIST third. So the idea is that this network has to learn to do sequence prediction and remember how to do its previous sequence prediction before it. Now, many of you are probably familiar with standard metrics for lifelong learning because we typically look at classification, so average accuracy, backward transfer, and other functions and other metrics. Here, we don't necessarily have that benefit for, at the time, continuous functions, so we just report the task matrices, and specifically, we report the lower left triangle. So the main diagonal is just the performance on the task, given the task. So again, we train the TNCN on Bouncing MNIST. It gets a squared error. Of course, we did smaller models, so the results are a little bit different than the earlier table. It gets a quick error of 102 on task 1. Then we move on to task 2, and it gets a squared error of 215, and then a squared error of 93. But if you look at the first column, what we would not want to see is we don't want that squared error to go up. Ideally, we want it to stay the same or even go down in this case. So we're actually seeing a little bit of positive forward transfer, which is kind of funny. It means as we trained on letters and NotMNIST and clothing items, it actually slightly improved its performance. There really is no inherent knowledge transfer I can think of from clothing back to simple objects. But again, it's encouraging to see that the squared error didn't change too much. And it does rise a little bit on NotMNIST. But we see here that for the LSTM trained with backprop through time and SAB and ARTS real-time recurrent learning, the squared error does rise. It doesn't rise drastically, but again, rising even just a little bit can be problematic because it means that we're seeing blurry samples, and now we're seeing extremely blurry samples, or the model is just outproducing maybe even weird garbage at certain frames, which mess with its metric evaluation. So it's encouraging to see that the P-TNCN, without any extra modification, no extra long-term memory and other components that I firmly believe are necessary for lifelong learning, is actually relatively robust for these benchmarks. And again, we quantified the zero-shot adaptation results on training the model on NotMNIST and testing it on Bouncing MNIST and vice versa. So that's what that arrow means. So here we looked at the same algorithms, the same model, and we said, okay, it gets, just look at squared error because cross entropy is usually higher in that. We see that, for example, the temporal neural coding network actually outperforms all the baselines after being trained on NotMNIST. So that means it wasn't trained on any of the sequences on Bouncing MNIST, which is very interesting. We also see the flip. If we train it on MNIST and then evaluate it exclusively on NotMNIST, that means that the P-TNCN still does well. Why is this happening? Well, we hypothesized in the paper and have since been prodding at that more over the year, is that the idea is that maybe the temporal neural coding network is learning something kind of like a meta-learning approach. The idea is that it's learning to error correct rather than learning something that's data dependent like an LSTM is. And again, if you think about what backprop and SAB are doing, they are creating an error signal at the output layer and then trying to do the credit assignment problem or blame the neurons for how far they contribute to the error signal at the output by doing calculus and calculating gradients. But this only happens during the training phase. During the testing phase, there's no correction at all happening. The model itself is only doing its raw prediction, whereas a temporal neural coding network, when you turn off the learning, because you can set the learning rate to 0, which is what we do for the test set of all of these, the neural coding network still has state correction. So even though it has to do what every other RNN model does, it has to guess what's at time step t, it's allowed then to look at the input, at least to correct a mismatch signal to adjust its own internal state, which is what any agent would actually do. If I were, again, thinking of a conversation example, I guess what word you were going to say, and let's say we were talking about neural networks, and all of a sudden Vincenzo starts talking about elephants. Well, I will have a high amount of surprisal, which is a term I borrow from cognitive science, so I'm going to have high error because I wasn't guessing that he was going to talk about an elephant, so I have a lot of error, and I can adjust my own internal state. It doesn't necessarily even mean I have to adjust my synaptic weights, although I hypothesize that even a little bit of learning is happening, maybe at a much lower rate than in some cases. But we can see here that that's why we're able to do zero-shot adaptation. So my hypothesis currently is that we are learning to do the process of error correction as opposed to just learning only data-dependent statistics, which is why we're able to see, for example, in our samples, models that are trained, again, these were trained on digits. Now, the LSTM doesn't do terrible, but the reason why its error is higher is you can see, first of all, a lot of kind of garbage in the background here. And again, these samples could be made clearer at the time that they were trained. You know, we could have used different loss functions and things like that to improve their performance. But what's interesting about this example I always liked is that as it's trying to predict the bouncing trajectory of the letters A and I, you see it, you know, doing okay. It's very noisy. And then it kind of collapses them to the digit 4. which is a very weird kind of thing that happened. And again, we saw this in a couple other samples and other weird examples. The LSTM doesn't do very well when you also change the number of objects. It does okay, but the P-TNCN is much clearer, and it's still able to get that point where the A and the I intersect. I mean, again, you could argue that there's room for improvement, but again, it's still able to maintain those objects. And remember, these things were not trained on bouncing characters. Now, we also have some results in the paper. I think I might have included them. Well, I think I have them in a bonus slide. We did one-shot learning as well, or one-shot tuning, where we also allowed the network, the LSTMs and the temporal neural coding networks to adapt on an intermediate data set. So we allowed them to tune on NotMNIST. That improves everyone's squared error, but again, the P-TNCN still outperformed it, which is kind of nice. You can imagine that you have an agent that's got this nice inductive bias by being pre-trained on pixels of different simulation environments, and now it's in an environment that it hasn't seen before, but that environment might share similar properties to things that the agent has seen before. So the agent should be able to leverage its prior knowledge to do zero-shot adaptation and quickly kind of make a mental picture, even if it's not the best picture. And then if we allow learning to happen, it can adjust itself pretty quickly. This might be useful for low data regimes, or improving the data efficiency of neural networks, something to investigate down the road. So I've kind of thrown a bunch of different ideas at you about the neural coding framework in minimizing total discrepancy, but it's kind of nice. There's a broader view of this general framework. I've talked to you largely about temporal modeling, but minimizing total discrepancy actually kind of affects many different areas, and there's even more that are not necessarily listed on the slide. So I have some pointers to some work, and I don't know if Vincenzo has we send slides, but I can include references, the actual references in these in a later slide. For large-scale classification, we've trained residual networks, or residual-like networks on ImageNet, and gotten matching relatively state-of-the-art performance with versions of an algorithm called recursive LRA. Again, the title of the paper, of the IEEE paper, says aligning representation. So essentially that just means that we're taking our guess state and making it closer to a target. What's nice is you can train big feed-forward networks actually pretty quickly for large-scale classification. So that's a nice benefit. Again, what's neat is that I'll show you a brief result in the next slide for online cumulative learning, which is a problem in lifelong learning where we are training an agent to do classification, but it's encountering new classes incrementally across tasks. What I mean by online is you're not allowed multiple epochs. So you're not allowed to store data, as we are not able as humans to store previous pixels of light that have entered our eyes. We have to make use of the information immediately and then create memory internally. So there's some interesting things you can do with the temporal neural coding network, adding lateral inhibition and adding other things like task-driven sparsity. Sparsity plays a really important role in that work, and there's going to be an update to that paper as well. The nice thing about the neural coding framework is it actually, with a few extra adjustments, generalizes to spiking networks. Because the network can handle discrete functions, we can now transmit bits. And so if the target for any layer was a binary vector, because we have maybe a more biophysically realistic neuron like the leaky integrate and fire neuron, which is what I play with in this paper below, the 2019 archive submission, that's going to have some updated results too. You can actually now create a learning signal. And it's kind of neat because most spiking neural networks are feed forward in nature. They take an input, they do a mapping, and they try to do some type of prediction. Whereas, again, we're thinking of this like top-down model, maybe with autoregressive connections, maybe not. But the idea is this thing is trying to guess either a sensory input that's encoded as a Poisson spike train, or spike trains that are encoding the activities of layers intermediate of the network. So it's really neat that this generalized in that direction. And the nice thing about that framework is that you could also leave behind leaky integrate and fire neurons and go with, for those of you who've heard of Eshkovit neurons or Hodgin-Huxley models, you can actually integrate those very easily into the framework as well. It's agnostic to the biophysical neuron that you use. And as we saw today, we can do continual temporal modeling. Now, admittedly, the benchmarks that I showed you were just, grayscale images of, bouncing balls or bouncing digits with, nice clean background images as well. So we're currently working on trying to look at more complex problems with natural images. If we wanted to use this in like a self-driving car or an autonomous vehicle, we would need to be dealing with background clutter and other objects as well. So that's kind of down the pipeline. Again, it's obscured by the preview thing, but I have a little plug for a paper. Keep your eyes out for the next coming week. I've been working on investigating the properties of the neural coding network as a generative model. Predictive coding in general is argued to be a generative model, but while it does have a nice probabilistic interpretation, I kind of showed you the linear algebra interpretation. You are essentially doing some version of variational Bayesian inference. The idea is that, the problem that I've noticed in most prior work is that they don't actually investigate the predictive coding framework as an actual generative synthesizer. What are the samples that this thing generates? Turns out that the neural coding network, with some nice connections to lateral inhibition, actually produce some pretty high quality samples. And so keep your eye out on that paper because it actually is a little bit more faithful to Carl Friston's free energy principle. I've integrated a couple other things into the framework. Just to whet your appetite in case you guys ever want another talk from me on online cumulative learning. So we basically can take the neural coding network, and I'm just showing you a very high level diagram. If we think about the recurrent weights as maybe lateral inhibition weights, so that means we're processing an input X, so again, a static image now, and some label that goes with it. So we're doing supervised learning. We can imagine that the network is maybe 2 layers. Again, it has its error neurons. What we want is to avoid crosstalk between neurons, which is argued to be one of the problems classically behind catastrophic interference. That means that neurons are being reused for multiple tasks when they really shouldn't be. There should be some specialization. We know that the properties of binary codes put you in a space that codes are kind of far from each other in some sense, so they're not going to overwrite each other as much. They're rather robust to noise. We want to induce sparsity in the network. So one thought we had was we could take the neural coding network, and it actually turns out that if we use something like a k-winner-take-all function or a ReLU activation function, it turns out that alone actually reduces the forgetting. But to get the benchmark results that we see here below, and again, it's unfortunately obscured, but the slides will be available later. You can also find this on the archive paper, the updated one, because I don't have these benchmark results on the old one. We compare to some state-of-the-art models, incremental moment matching, hard attention to task, which are state-of-the-art, slightly biophysically realistic in some ideas, back-propagation models. We also took those benchmarks and implemented them ourselves and tried to train them in an online fashion. As most state-of-the-art lifelong learning assumes you can do multiple epochs through a data set, although I've seen some online variations. So their performance naturally goes down. We're just reporting here average accuracy, but we also will update with backward transfer and some other forgetting metrics. We can see here that the neural coding network at the bottom, one version of our model, actually outperforms all of them. Now, the only caveat to this particular model is while we do reduce forgetting when we add lateral inhibition and induce sparsity, we needed to introduce sort of another complementary network that is called the context model. And it's nice because it has some connections to the basal ganglia, which does task execution. The idea is that this model actually is maybe conditioned on just the input X. And the idea is that its task is to produce a context representation of a task T. And this will then change or mediate the sparsity pattern. So we kind of want certain neurons, if we just have all the neurons kind of sparsely aggregated, let's say you have a small network and not a massive network with large access to resources, even with sparse patterns, as I've noticed experimentally, sometimes even with small changes to the synaptic weights with any update rule, can perturb the performance on old tasks and start inducing a large undesirable amount of forgetting. So the idea I thought was, why not have a task model kind of start to learn and lock in on certain neurons for a certain task. So we sort of learn separable representations, or like classically known semi-distributed representations that are orthogonal to each other, so that way the neurons don't override and talk to each other too much. In short, you can see here in this particular slide, 3 neurons were selected for the current task, mediated by the context model. And so what's nice is that even though you'll see a little gradual forgetting, which is acceptable in a cognitively plausible agent for catastrophic forgetting, this actually reduces significantly the crosstalk between neurons, and we actually preserve knowledge on task 1, and then the network kind of learns to select a different sub-network. Since the brain is sparse, it kind of implies that only a few neurons are firing for a task. And so we actually can learn quite a few tasks within a fixed capacity network. This network, again, in the paper, we admit that we did not do any neurogenesis, so we did not grow new weights or do too much in terms of pruning. So that's a nice extension to the model, which would allow it to potentially generalize to infinite tasks. And so there's a lot of interesting work that needs to be done on the model. We looked at, again, non-MNIST, MNIST, fashion MNIST. We created them as the split MNIST benchmark. And we also have a nice hard benchmark in the paper that's already on archive, where a lot of these baselines we also compare to EWC and other ones that you might be familiar with, which break down when you have variable number of output classes. And again, that can be topic for a longer talk, a different talk. So we finally reached a summary, and apologize for going a bit long here, a lot to say. But the idea here is that by challenging the fundamental way that artificial neural networks are trained, that is backprop, there might be a path forward to designing agents or intelligent systems that that combat hard problems such as continuous sequence modeling, and as I presented, maybe even other continual classification learning problems or incremental class learning. The idea is that we are now free from having to please backprop. And by introducing a more biophysically realistic learning rule, and there are still many details missing in that bio picture. A neuroscientist would easily be able to pick out many things that are missing in the current algorithm, but I'm confident that those mechanisms can be introduced because we, again, are not constrained, for example, by the need for a differentiable activation function. The spiking network was a nice step forward to generalizing the network to communicating with bits. Total discrepancy function, total discrepancy optimization, as I've mentioned, kind of creates a nice flexible framework for integrating even mechanisms like lateral inhibition that might help us get neural agents that generalize differently. And again, the way I see catastrophic interference is that it kind of hints at that, well, we're able to train nice narrow AI or agents that are specialized for a certain task. If we want to get the agents to do things that are arguably slightly more human realistic, like learning different pattern tasks and aggregating knowledge and transferring knowledge and kind of learning sort of like an internal knowledge base, we're going to need to challenge the way that most of artificial neural networks work today. And I think local learning rules that are motivated from a nice grounded theoretical framework like the free energy principle allows this. And of course, this kind of creates a nice beginning bridge between computational neuroscience, cognitive science, and statistical learning to tackle the grand challenge of lifelong learning. There are many avenues for improvement, and there's certainly many criticisms in the current models I have presented. There are certain additional biological constraints that are annoying that I would like to introduce that I don't have. For example, I still allow the synapses to be negative or positive. And we know that the synaptic weights in the brain would be modeled more likely by a positive value. There shouldn't be negative values. So that would mean we need to introduce interhibitory and inhibitory neurons in order to allow depression and suppression. There's no reason why that wouldn't work in this framework, but that requires some investigation. And again, generalizing this to other types of problems. Right now, the agents I've been training, you could argue are reactive. They just kind of take a pattern and they say, okay, I'm going to predict what I think it is, but they're just learning a quasi-generative model or a generative model of their sensory environment. but they don't do anything. They don't have any impetus of their own, so trying to combine this in a reward-based learning framework would be nice, and predictive coding allows that active inference approach, so this can be generalized in that direction, but it requires research. And then, of course, there's other things like, even, for example, some of the models I played with use task descriptors, and it'd be nice to get rid of them, but the task context model gets rid of that. Investigating the limitations of the models on massive sequences. What happens if I'm training the P-TNCN on 1,000 different sequence modeling problems? Even though it has the potential to do online and zero-shot adaptation, I am certain that the basic model is going to forget after a certain point. So we need to introduce things like dynamic model capacity. Neurogenesis would be an important component. Long-term memory components are important. We know that the brain has different types of memory, and the idea is that we want to be able to emulate some of that. There's no reason why you couldn't extend the neural coding framework to that. Robustness to fuzzy task boundaries. There's been some research in lifelong learning where the boundaries between like classifying digits and classifying clothing, there might be mixing samples through time. So that's something interesting, or looking at streams that are more typical in robotics. And again, many other machine learning problems could be recast as continual learning problems. Since this is kind of offered a framework to attack sequence modeling, this might be useful for tackling more complex problems. And I have reached the end. So any questions?
Thank you so much, Alex, for your very interesting presentation. So maybe I can start with a simple question. But do you have basic, maybe PyTorch implementation of your algorithm that we can look at and we can use?
So unfortunately, when we released the IEEE article, we have a link to a GitHub called Continual P-TNCN. So I actually wanted to have that up by the time of this talk, but I will be putting it up this weekend. So there is an implementation to play with Penn Treebank. We also have one of our baselines implemented in TensorFlow. So I have I coded up the P-TNCN in TensorFlow. And the nice thing about the update rules is that you don't technically need much of these frameworks, since you don't need gradient tape or any of the backprop procedures. You only need the linear algebra. So the funny thing about the way that my collaborator, longtime friend Ankur, and I do is we actually use the linear algebra component of most of these libraries. So again, we also, I think the SAB is also in TensorFlow, but we have coded up the model in PyTorch as well. But it's in TensorFlow too. So again, the equations are very explicit. It's just using the basic linear algebra. Recursive LRA, we will be releasing soon as well for those that are interested in the large scale classification aspect. And to complement my generative model, I will be releasing some code in the near future once I get that paper out. The spiking neural network, I'm still waiting on publication, so I haven't released the TensorFlow code to back it. But I will be releasing the P-TNCN and the lifelong learning paper in the near future. The P-TNCN should come out this weekend, so you'll have TensorFlow code to play with.
That will be great. And then another question is, I noticed a few aspects with the, I don't know if you know it, the hierarchical temporal memory models that have been proposed by Subodh Ahmed and Jeff Hawkins from Numenta. I don't know if you know about this model, but it shares a lot of interesting ideas with your model as well, I think.
Yeah, Numenta. What were you saying though earlier? I heard Numenta. I know if there were.
The hierarchical temporal memory models. I mean, the algorithms that I think they have some interesting shared aspects with your algorithms. So if you know, if you have a more clear idea on what are the aspects that are more similar and how they can be related.
I think the part that I shared the greatest similarity, and actually I was aware of those papers too throughout the years of this work, is sparsity. Now, while the temporal neurocoding network, and I do mention it, I believe in one of the papers related to it, has what I call a weak kind of penalty to encourage sparsity. So when you impose like a Laplacian prior or an L1 penalty, as I showed you in the math of this talk, that while that does encourage many neurons to kind of, be close to zero, and only a few being non-zero to kind of learn kind of sparse kind of causal factor-like representations, there are problems with that penalty. And so the work that I have done that I briefly showed at the end on the lifelong learning or the lifelong classification problem, that one induces a lot of sparsity. And so I think in that one I share kind of similarity in the sense that the motivation for learning sparse codes and the fact that they don't overlap too much kind of rests on that idea that we don't want too much crosstalk between neurons. And so we want to rely heavily on sparse activity patterns. The way I understand their scheme too is that they also do design though like feed forward like models, where I would say mine has a more of a top down kind of flavor to it. You might be able to give me more insight because I only am aware of like their sparsity work. I don't think that they're predicting, are they predicting every layer or not? I will admit that I'm not familiar with their exact learning scheme.
Yeah, I think that, so for example, they use this idea of that a neuron can have also a predictive, let's say, state in which is more probable to fire somehow, and so the idea still for them is to predict the next, let's say, state of each neuron. So yeah.
Okay, so then there's a similarity then that would be, if they're doing that, then there is a similarity between what this network is sort of doing as well. The temporal neural coding network, sorry for interrupting you there, but the recurrent weights, you could argue, are also doing that. They are taking the information from the last state, and they are effectively, so another interesting historical perspective to this work and the work that I build on top of is you could also view in some ways the neural coding network as a Kalman filter. And so when you derive a deep Kalman filter in some ways, if you derive the update rules for the recurrent weights, you are seeing that the recurrent weights guess the current state, and then there is a corrected state that allows you to do that extra signal. And I had them as the green diamonds in my talk. In that sense, I'd say that has strong similarities with the work in Numenta. And I also do want to mention too, I think they were the ones that also talked about introducing the K-winner-take-all sparsity. Am I correct about that?
Yeah, very recently, I think.
The lifelong learning work that I have in 2019, the continual learning benchmark one, that one also plays a lot with the K-winner-take-all. I found that function to be a very useful approximation of lateral inhibition. Instead of having the lateral weights, you can just kind of, use this sort function and just pick the neurons with the most function. There is a difference, and I liked actually one thing that they have, which is that duty cycle. I actually think that would improve some of my own results, incorporating maybe that boosting factor. But we both share that function. And again, the idea is that you can model some complex lateral interactions with neurons with a relatively simple function. So I think that's another similarity that you just reminded me of.
Yeah, and then so since there are so many similarities, I know that they struggle to model, let's say, I-dimensional data. I mean, I see that you have worked with the images, but they really struggle to scale the algorithm up to somehow fix the credit assignment problem with the very I-dimensional data with these like local rules and without the propagation. So I wanted to know if in your algorithm you think this could be possible, scaling up the dimensionality of the data and solving the credit assignment problem, even though you don't have a long, propagation algorithm implemented.
Yes. The answer is yes. I do strongly suspect that this works well when scaling up. The empirical evidence I have so far to justify that actually was in my slide. It's not necessarily presented explicitly, but it was in that general kind of overview. The large scale classification. So in that paper, what we did was, while that was a residual architecture like framework looking at feed-forward networks, so we didn't have a temporal dimension in that problem, that one we had color channels. And so that's where the problem gets high dimensional. So if you just took the temporal neural coding network, as I've talked to you guys in these slides, you would have to concatenate the color channels. Now, there's no reason why I don't think this would generalize fine to very, very wide input spaces. It would just take longer because, again, the matrix multiplies, get bigger. I think that there's a more efficient way to do that. And this is where there is some nice connections to convolutional neural networks that I think can be brought in. So what we did in the large-scale learning paper is we came up with an update rule for a form of convolution that we coined as pseudo convolution, which is actually based on a paper called, it was a really neat little paper, Perturbative Neural Networks, where they proposed essentially using fixed noise maps to approximate the convolutional filter. And while you do pay a little bit of an extra memory cost to initialize these filters, the math actually reduces beautifully to almost like doing binary convolution with just learning a scalar weight per filter. And what was neat is that we thought, what if we took that convolutional rule and created a local learning rule for it? And that's what we did in the sort of total discrepancy framework. Came up with it actually reduces to a nice little Hebbian rule that takes the error neural signal that would come out of the output of the filter and collapses it to a sum. So it just reduces it to a scalar update. So the rule's really simple. Turns out we can train those convolutional filters with an error Hebbian rule that's used very much like in the neural coding network. That allowed us to train with a large number of filters in large blocks. So we actually trained, of course, it's not the biggest one that exists, but we trained a ResNet 18. So the 18 residual blocks with a couple of different operations in there. I think the details are in the new appendix of the paper with how many filters are in every layer. We were able to scale 2 color channels. Now, of course, that was an X to Y problem. But ImageNet, which is the nice result that we got on that, and we actually matched the performance of back-propagation and outperformed all the other biologically inspired alternatives like sign signal, feedback alignment, difference target prop. We matched back prop though, which is saying, well, okay, we're competitive. The nice thing about that was that we could scale to high dimensional inputs. So the thing we haven't done yet, but we are looking at that actively, is could we then take that rule, that pseudo-convolutional rule, and develop a deconvolutional version? Because the neural coding network, the way I present it to you guys, is like a top-down generative model. So it's guessing those high-dimensional inputs. So I think while it would be fine, you could just concatenate the color channels and try to learn the fully connected matrix, I do think a locally connected structure, which we do know is in cortical regions of the brain, of the eye. For example, we know that things are locally connected. They don't necessarily work like a proper convolution, but they approximate it. I think that rule combined in this framework would allow it to scale naturally to very high dimensional images. The other evidence I have for this, although it's not yet published, is that if you train it on high dimensional sparse encodings, so if you're training on language has this problem where if we're doing language modeling, you have thousands and thousands, tens of thousands, hundreds of thousands of class targets. While it's very sparse, and you could take advantage of that sparsity in some weird ways with the error neurons, you still have to assign a log probability to all possible classes. And so the nice thing is there are some ways to generalize the neural coding network to tackle these high dimensional spaces. So I have some very preliminary, it's not published yet, evidence that you can tackle large class spaces, but it still remains to be investigated to see how does my hypothesis that, using something like a pseudo convolution or a locally connected structure allows it to deal with high dimensional spaces. But I would say it would probably generalize.
Well, that's very promising and interesting. So we'll take a look at your papers as soon as you publish them.
Yeah, and I would encourage anyone to play with these models. There's a lot to tweak and a lot to change. I think it just opens up some nice doors because, for example, those of you that might be working on applications where you might be struggling, and again, I'm not going to say this is a silver bullet. I am very well aware the no free lunch theorem applies to even locally inspired, local learning algorithms as well. What this might open the door is allowing you to introduce mechanisms for your problem that are not necessarily to help backprop. So, like I said, I think the nicest example is if you want to train something with discrete variables, this would allow you to do that. And actually in the appendix of this paper, although I've been investigating that more in follow-up work, is I trained it with signum activation function. So again, the derivative of that is a Dirac delta function if you were to do backprop, which is basically garbage. You can't train the network. But let's say you need discrete representations because you're doing something like symbolic processing. I would say that learning rules that are based on like total discrepancy and rules like this open the door to designing architectures that have naturally discrete components that if you were forced to approximate them with something like the reinforce algorithm or biased estimators, they might introduce error that you don't want into your system. So I think this is another nice attractive property that is something to explore. I'm sure that there are limitations to this model, but and it definitely needs, even though I was surprised, and I know you didn't necessarily ask this, but I just wanted to mention it. While I was surprised and happy with its zero-shot capability, there's still a lot of room for improvement in terms of the metrics. And I also don't like that it doesn't have a longer-term memory component. And I think integrating that would be important, especially to tackle more complex tasks. But there's no reason why it would fit. The nice thing about neural coding is that it tries to get out of your way. As long as you commit to a few assumptions, you commit to, we're minimizing this kind of total discrepancy function and we're going to have error neurons, because if you don't have the error neurons, obviously this doesn't work. If you commit to that assumption, you can kind of put whatever you want in between these layers. And actually, another thing I'll mention for those that want to play with it is you could mix backprop in this framework. While I try in all my work to not use any kind of gradient rules like that anymore because it's not what happens in the brain, there's no reason you couldn't. You could imagine that those little like locally connected networks are deep feed-forward networks, and you want to take the error signal that's produced by an error neuron, you could backpropagate it. You could use Hebbian rules in there as well. So it's kind of neat because it opens the door to mixing other algorithms in that framework as well. If you're finding that the assumptions that the basic temporal neural coding network are too limiting for your problem. So I just wanted to kind of mention that because I think that's ripe for exploration, and there's a lot of nice tie-ins. Like, for example, you could imagine doing an intermediate hybrid between neural coding and backprop if you want to train some complex intermediate model in the layers.
Yeah. So thanks. And do we have any other question from the other people that I see here? Okay, so thank you again, Alex, for joining us today. And
thank you for having me.
I invite you to, if you can, if you want, to share a link to your uploaded slides to me, so that I can also create a topic inside our forum, and then maybe this discussion can proceed there. And of course, I will upload this video, and I'll send you the link afterwards. So you're all invited to check these resources after the end of this session. So thank you all again for joining, and I hope to see you again next week for the next reading group session. So thank you again.
Thank you for having me. It was my pleasure.
Bye. Bye, everybody.
Bye. Stay safe, everyone.
Stay safe.
Thank you for the talk.
Bye.
Thanks.